Okay, so good evening everyone and welcome to the fifth session for the course Introductory course in Real Analysis. Okay, so let's start with the problem of sequence. So we have a sequence given as cos 1 by n. Okay, and now you have to choose like which of the following among these are a subsequence of the sequence cos 1 by n. So just so do you know the definition of sequence? So suppose this is a sequence given to you. Okay, then I hope you must be knowing. I'm just telling you once again. So this is a subsequence if like this n1. So here the k is varying, k from 1 to infinity. Okay, so this is just the notation. Okay, this nk, n sub k. So this is a subsequence if this n1 is less than n2 is less than n3. Like you have this increasing order. Okay, and each xnk should belong to this sequence, right? So xn, n from 1 to infinity. So these x and k should be member of from this sequence. It cannot be anything arbitrary, but it has to be an element from the sequence xn. Okay, so this is what we mean by subsequence. So in this particular problem you have to tell like which of the following is the subsequence of this cos 1 by n. Okay, so like to begin with, let's start with the first one. So so basically to tell that which of the following is a subsequence, you see cos is common in everyone. Okay, so what you have to basically find that, so from here you can say that 1 by sin n, this one. So the question reduces to saying that which of the following plus 1 is a subsequence or R subsequence of 1 by n, right? So this is the reduced question. So you just forget about cos. There is nothing special about cos. So basically you have to tell that the subsequence which of the following among these four are subsequence of 1 by n. In other words, like equivalently you can say that sin n root n 2 raised to the power n and log n plus 1 is a or are subsequence of n, right? So this is another equivalent thing. Okay, so you have to tell me which of the following is a subsequence of n. Now the problem is much more easier. Just looking at it you can tell me, right, which of the following is a subsequence of n. So what is the sequence n? Okay, just let me just copy this up. Okay, so now you tell me what is the sequence n. So n is nothing but like just natural number 1 2 3 4 5 6 and so on, right? Now when you look at this sin n, okay, so sin n would be sin 1 sin 2 sin 3 and so on. Now clearly if you look at this, the very basic thing, this sin 1, the value of sin 1 is not going to be a natural number, right? Sin 1 is 0 point something something. Okay, so it's a decimal value, so this does not belong to natural number. Okay, so this cannot be a subsequence. So this is not a subsequence of n, correct? Similarly, if you look at root n, so what is this sequence? It is 1 root 2 root 3 and so on. Clearly this is also not a subsequence of n, right? Because root 2 is a decimal value 1.44, so 414 like that, correct? So this is also not going to be a subsequence of n. Similarly, if you look at this log n plus 1, so what is this sequence? So it is log 2 log 3 log 4 and so on. Over here also the value of log 2 is not integer, right? So or not a natural number, so this also does not belong to n, this also does not belong to n. So this is not a subsequence of n, right? Now if we look at this, this one 2 raised to the power n, so like whatever the value, so if you just note it down, 2 raised to the power n is 2, 4, 8, right? All these are subset of, if you look at n, are subset of natural number, or in other words the sequence n, right? So this, so this cos 1 by 2 raised to the power n is a subsequence of cos 1 by n, right? So this was an easy warm-up problem for related to sequence. Okay, so it's an easy, so the correct answer would be this C, right? Others are not a subsequence of this cos 1 by n. Okay, so now let's move to another problem again related to sequence. So this is maybe a bit kind of new for you guys, like you might have not seen this kind of example. So over here so you have been given this alpha beta gamma to be a positive real number, right? So alpha beta gamma are greater than 0. Moreover, it has been given that this alpha beta gamma satisfies this condition such that alpha beta plus gamma, this is less than equal to 1. Right? So you have this bound as well on this alpha beta gamma, correct? Then you define the sequence. Okay, so how do you define this? So you assign the first sequential value is alpha. Okay, after this you just define it recursively as Pn upon alpha Pn plus gamma, sorry, this is beta. So this is how you define the other terms of the sequence. Okay, so P1 is given as alpha, then you can define P2. So this is for n belonging to natural number. So you can define P2 and then P3 and then P4, right? So it's a recursive definition that you have. So in one of the session I discussed that how to find the limit of such sequences. You just take limit and then you solve the equation whatever you get, right? So we'll ultimately do that, but before going to that part we have to just first make sure that this sequence converge. And once this sequence, if we can show that this sequence converge, then you have to find the limit. Okay, so first you have to show that it converges and then you have to show what will be the limit. So you have to find the limit, and finding limit is easy. Okay, so the main problem is to show that this sequence Pn defined in this fashion is a convergent sequence. Okay, so that is the main issue or the main part of this problem. Okay, so like to solve this one, so what I'll be using is this monotone convergence theorem, that you have to show that this Pn, okay, is an increasing bounded sequence. If I show that, then we'll get that, okay, this is a convergent sequence. Okay, so this is based on this monotone convergence theorem. Like I'll show with that, maybe there could be other method as well. Okay, so I am using this monotone convergence theorem to prove the convergency of this series. Okay, so to begin with so what do we need to show in this one? We have to show that this sequence Pn is bounded and monotonically increasing. Okay, if you can show decreasing as well, that is fine, but over here we have this monotonically increasing sequence. Okay, so this is our goal. So we will show that Pn is bounded and the sequence Pn is increasing. Okay. Okay, so first note that, okay, so this would be just a point. So first note that P1 you can clearly see it is greater than 0, right? Now once, so let me write P1 is greater than 0 and then P2 is again greater than 0 because this is greater than 0 for n equal to 1 I am saying, and this is greater than 0. So this denominator and numerator all are strictly greater than 0. So P2 is greater than 0. Again in a similar fashion, P3 is greater than 0. P4 is greater than 0. Okay. So if you notice over here, If I just use this identity definition, so you can see that this Pn plus 1 equal to 0 implies, or I can directly say that it is greater than 0. There is nothing to write. Okay, so P1 is greater than 0, and from here you can say that Pn plus 1 is greater than 0 for all n belonging to n. Okay, you can even prove by induction, like, but it's obvious over here, like you don't have to prove anything. So all the sequential terms is a positive, so this sequence is a sequence of positive real number. That is the first thing. Okay, now as I said that I'll show that this sequence Pn is bounded and it's monotonically increasing. Okay, so let's first prove that Pn is bounded. So maybe so we'll show, or let me write it as a claim. Claim is that Pn is bounded. Okay, so the proof is not much difficult. You can see from here. So if you look at this identity, how we define Pn plus 1. So like you just take 1 by Pn plus 1. Okay, so 1 by Pn plus 1 is beta Pn plus gamma upon Pn. Like I did this just to, so that I can split this numerator part. Okay, so once when I split this addition, so I'll get beta plus gamma by Pn, right? Now I know that this term is greater than 0, right? So from here I can say that this is greater than beta. So this would imply that Pn plus 1 is less than 1 by beta. And also we know that Pn plus 1 is a positive. So this kind of bound we have. This is for all n belonging to natural number, right? So we have that the sequence Pn, okay, that is a bounded sequence, right? So this shows the sequence Pn is bounded. Okay, now what I was saying, that I'll show that it is a monotonically increasing sequence. Okay, so let's go to that. So another claim would be that Pn is monotonically increasing sequence. Okay, again this proof is again easy, you don't have to do much stuff. So to prove that it is increasing, basically you have to show that the difference Pn plus 1 minus Pn is greater than equal to 0, right? This is what we need to show, correct? Because this is equivalent as saying this Pn plus 1 is greater than equal to Pn, or strictly greater than. If you just want strict, that's you put just a strict inequality. Okay, so over here let us see what is this Pn plus 1 minus Pn, what will be the value. So Pn plus 1, the definition we know, it is Pn upon, so what we have is Pn upon beta Pn plus gamma, and then you have to subtract Pn, correct? So this is the difference what we have of the two terms. Now what we can do is just take Pn common, then we have 1 by beta Pn plus gamma minus 1. Now you just take the LCM, just if you subtract, what you get is beta Pn plus gamma, then you have 1 minus beta Pn plus gamma. Right? Yeah, okay. Now what we can do is, if you look here, this Pn, we know it is strictly greater than 0, correct? And now I think I'll have to use some condition over here. Okay, over here so this numerator is greater than 0, this part is also greater than 0, correct? We don't have any issue over here. Now what we need to make sure is that this part is greater than 0. Okay. And how to show that? So we have been given that this condition. Okay, so let me see how we can use it. Okay, so I'll have to check. So we have alpha beta plus gamma is less than equal to 1. That means that 1 minus alpha beta minus gamma is greater than equal to 0. Okay, so if I use this one here, so you can clearly see that P2 minus P1, if I just do P2 minus P1, okay, let me just do P2 minus P1, then I have P1, then 1 minus, so this P1 will become alpha beta plus gamma, and then in the denominator you have alpha beta plus gamma, right? And now I know that this is greater than 0. Okay, so this whole thing is greater than 0. So clearly P2 is, so this will show you that P2 is strictly greater than P1, but you have to show it recursively. So what we can do, as you can see here, I want to prove that beta Pn plus gamma, so this will be greater than 0 if and only if beta Pn plus gamma minus plus 1 is greater than 0. So this is less than equal to 1. This is what we need to prove. Okay, so how to prove it? So maybe we'll have to use this part. So what we can do is, so my claim would be, so just let me see what one can do. So claim would be that beta Pn plus gamma is less than equal to 1. Okay, so let me see how to prove this one. So it's clear that for p n equal to 1 this is true. So I will try to prove it by induction. So for n equal to 1, I know that beta p1 plus gamma, which is alpha beta gamma, is less than equal to 1. That we know, correct? And the next one is for, so assume it is true for n. So now we'll prove it for n plus 1. So we prove for n plus 1. Okay, so we have beta Pn plus 1 plus gamma. So let me write the definition. So we have beta Pn beta plus gamma, and then you have gamma, right? So from here what we can get is so just beta Pn, again I think, okay, let's see. So beta Pn plus gamma into beta Pn plus gamma by Pn beta plus gamma, right? Then what we have is gamma square plus beta Pn gamma plus beta Pn. Okay, or what we can do is, so we have to show, so I'll have to use that beta Pn plus gamma is less than equal to 1. So am I getting such terms over here, beta Pn plus gamma? Yeah, I think so. Just a second. So from here I can use is beta Pn plus gamma less than equal to 1. So I'll get beta Pn plus gamma into 1 upon beta Pn plus gamma, and this is equal to 1. Okay, so here I am using the induction, this term, I mean this fact, right? So using this over here. Okay, So I got this one. So what I proved is, so this claim is proved. Okay. So this beta Pn plus gamma is less than equal to n for all n belonging to natural number. Okay. So now I don't need all these things. Okay. So see over here, this is the place where I have used this condition. This condition alpha beta plus gamma less than equal to 1. This is the place, because I need to make sure that the induction space, so for the base space which is n equal to 1, it should be true. Then I assumed it to be true for n, and then I proved that this is in true for n plus 1. So by the induction we have the proof. Okay. Okay, so this we have. So over here what we can say is this whole part is greater than 0, right? So this is okay, I can make it greater than equal to 0. Okay, because this is greater than equal to 0. Okay, so what we have is this Pn plus 1 minus Pn is greater than equal to 0, which is nothing but saying that this implies that the sequence Pn is monotonically increasing. Okay, so we have that Pn is bounded and then Pn is monotonically increasing, and hence, so let me put it in the bracket maybe. Okay, so by monotone convergence theorem, we have that the sequence Pn is convergent. Okay, so is this clear? Like what I have shown is just two things. Okay, so the first thing what I showed, that Pn is bounded. Okay, and in this case we just use the fact that Pn is strictly greater than 0. Okay, so why okay, so this point why I proved that Pn is strictly greater than 0, because you see over here I had to divide it by Pn, right? Everywhere if you see here I had to divide it by Pn, so it should make sense that it should, if it is 0 then we are gone, we cannot do this, we cannot take reciprocal and all. So this is one of the reason, and also we have used the fact that this is greater than 0 to prove that Pn is a bounded sequence. Okay, so this is the place where I have used the fact that this alpha is greater than 0. If you notice that this alpha is greater than 0 is making P2 greater than 0. So you see, if you notice from here, P1 which is alpha greater than 0 implies that P2 is greater than 0, which implies P3 is greater than 0, and so on, right? So here I have used the fact that alpha is greater than 0. Okay, now beta greater than 0 is being used here. If you notice here, beta is greater than 0, I have used here, right, to get such bound. If over here also if beta is equal to 0, then we are gone, then we cannot show that Pn is bounded. Okay, so this is another place, and the fact that alpha beta plus gamma less than equal to 1 is being used here at this place, right? Because I use that fact to prove that this beta Pn plus gamma is less than equal to 1 for all n. So that has been used here. So in this whole proof I have just shown that Pn is bounded and then Pn is monotonically increasing. While proving these two things we needed something else. For example, this estimate that beta Pn plus gamma is less than equal to 1, and we proved it. Okay, so overall the main thing is that we proved this Pn is bounded and Pn is monotonically increasing, and hence we get the result that the sequence Pn is convergent. Okay, now the question was to find the limit. So as I mentioned you earlier, finding limit is easier, right? So how do we find that? So just recall this definition. So let me just copy this one. Okay, so Pn is convergent, and let limit n going to infinity Pn is equal to P. Okay, so now Pn plus 1 is equal to this. So passing limit, we get passing limit n going to infinity, what we get is P is equal to P upon beta P plus gamma, right? So if we try to solve this one, so I'll get beta P square plus gamma P, and then equals to P, which is minus P, equal to 0, right? So over here I can take P common, so what I get is beta P plus gamma minus 1 is equal to 0. So this tells me that P is equal to 0, or P is equal to 1 minus gamma upon beta, right? So these are the two possibilities, that the limit, the sequence Pn will either converge to 0 or converge to this. Okay, but it cannot converge to two limits, so we have to discard one of the things, one of the options, right? So both of them cannot be possible. So over for that, what we can notice here is, you see, we have seen that, okay, so I think I can write it here. So Pn is convergent. So what does monotone convergence theorem says? That if it is an increasing sequence and it bounded, then it will converge to the supremum. So Pn is convergent and converges to its supremum, right? So we have this thing, that it will converge to the supremum value. Okay, now you tell me over here, is it possible that the supremum of this Pn is equal to 0? Can this happen? So you have already noticed this thing. So what we have noticed is Pn is greater than 0 for all n, and Pn is continuously increasing, right? So we know that P1 less than P2, so this is greater than 0, P3, like this it's going, it is increasing. So obviously supremum of this sequence cannot be 0. So this implies that, just this line, supremum of Pn is not equal to 0, and in fact it is greater than 0, right? That is for sure, and hence P cannot be 0, the limit, because the limit is, so hence P, which is equal to supremum or limit of Pn, and this is same as supremum of Pn, right? Because by monotone convergence theorem we know that the sequence converges to its supremum, and this is greater than 0, correct? And hence this proves that P cannot be 0, or in other words P is equal to 1 minus gamma upon beta. Okay, so this is the final answer for this problem. So the limit value will be this. Okay, is this fine, or do you have any doubt? Is everything okay?
Yes, sir.
Okay, so now I have one doubt. So can you make sure that how this P is greater than 0? Because I have mentioned that the supremum is always greater than 0. It cannot be less than 0, right? Because it is increasing.
All the terms in the sequence are greater than 0, sir.
Correct. But I am saying how this P, so I have got 1 minus gamma upon beta, right? So I am asking that 1 minus, so we know that beta is greater than 0. So P, the value of P is 1 minus gamma upon beta. I know this beta is greater than 0, but how do you make sure that this is greater than 0, 1 minus gamma. Did you get the question or not? Did you get the question or like not?
Yes, sir. Yes, sir.
Yeah, so
It is given that alpha, beta, gamma all are greater than 0.
correct,
And
but
alpha,
how do you
beta
make
plus
sure that?
gamma is less.
Yeah. Tell.
Alpha, beta plus gamma is less than 1. So 1 minus gamma should be greater than 0 only, no, sir?
Yeah, because this is greater than 0. Right? You're right. Correct. So that's why this 1 minus gamma is greater than 0. Okay. Good. Okay. So now if this is fine, let's proceed to the next problem. So again, so you have given a set S, okay, which is a non-empty subset of R, and it is bounded above. So the supremum exists. That's all we know, that this is the property of real number, right? So if we have a bounded subset of real number which is non-empty, then we know that the supremum will exist. So now I'm denoting the supremum by alpha. Okay. So now the question is that when you have a set, okay, with some supremum, then there exists so suppose this is a set, or let's take the interval AB. The best example would be, so this AB, now in this interval this B is the supremum, right? The question is that for this supremum there will exist a sequence, so there will exist xn's which will converge to this B. Okay, so when you have a supremum value, there will exist a sequence which will converge to that supremum value. Okay, is the question clear? Now can you just, is it understandable? I mean, can you get some hint, or can you get some feeling that okay, yes, this should be true, by just maybe by just the monotone convergence theorem, as I just mentioned, that see, when you have this S which is a bounded, okay, so S is a bounded subset, right? And so S has some supremum value. Now you have to just find a increasing sequence, right? If I find an increasing sequence in this set S, then obviously it will converge to the supremum value, that we already know. So we have to just find a increasing sequence. That's all we have to do. So it seems that it should be true, and I mean it is doable. We can obviously find some increasing sequence in that given set, right? Because we have the order property in the real line. We know that how to put some order, so we can choose the element properly to make it increasing. That's all we need to do. So we have to make an infinite sequence in such a way that it converges to the supremum value. Okay, so it seems that it should be true. Okay, now we'll go to the proof. Okay, so for the proof we'll just use the definition, okay, nothing more. So let me first write the definition. What do we mean by, so when we say alpha is the supremum of S, what does it mean? So it has two things, right? First thing is that it is an upper bound for the set S. That means x is less than equal to alpha for all x belonging to the set S. This is the first thing. The second thing is that if I decrease the value of supremum by some point, then I'll get an element of S which is greater than this. So nothing less than alpha can be an upper bound, right? So this is the first thing, that upper bound, and the second one is nothing less than alpha. So I'll just write it somewhere else. So nothing less than alpha can be an upper bound, right? And that's why we call it lowest upper bound, right? The minimum one from the lower bound, so for the upper bound, so least upper bound, right? So that means that for any epsilon greater than 0, there exists some x epsilon in S such that if I reduce the supremum by epsilon value, then I'll get this x epsilon, okay, which is greater than, strictly greater than this and less than equal to alpha, right? Because alpha is an upper bound, so this is anyway going to be true. So this is anyway true from the first point. Now the main thing is this line, that if I decrease the supremum value by small real number, whatever, how much small it can be, I'll get an element from the S which is strictly greater than that element, and it could be equal to alpha. Okay, so this is the definition of supremum. Now we'll try to use this definition to get a sequence which will converge to this alpha, right? So what we'll do, okay, so this was just the definition of supremum. Now, so using this epsilon property, or I mean this point, I'll try to get a sequence. So what we can do, we know that for each natural number n, okay, there will exist an xn belonging to S such that this xn, this alpha minus 1 by n is less than xn. I have just taken epsilon equal to 1 by n in the last line. That's all what I have done here. Okay, so I can get a sequence xn which is greater than alpha minus 1 by n, and obviously I know that this is less than equal to alpha. Now from here you can clearly see that if I just use the sandwich theorem or this squeeze theorem, we get that the sequence xn is convergent and the limit value is alpha. So this proves that limit of xn is equal to alpha. So this is by sandwich or squeeze theorem. Okay, so this proves that, so xn is a sequence converging to alpha, right? So if we have a supremum, just using the definition of supremum, we can construct a sequence xn which will converge to alpha. Okay, is this okay to everyone?
Yes, sir.
Okay, so now let's move to the next problem. Okay, so you have to choose the correct statement. Okay, so can you tell me which of the following is correct? I think this should be an easy one. What about the first line?
A is correct.
A is? Is it true or false, the first statement?
True, sir.
It is false, you are saying? Be confident, like you don't have to worry. What do you feel?
Answer
Sorry?
A is false.
Mean you are also saying true?
Sir, B is.
Okay, you are
True,
saying
sir.
B is true. Okay, that's fine. But someone said that A is also true. Do you agree or not? You are saying A is false, right? So can
Yes,
you give
sir.
some example for that? The example is the most common one, like there's nothing to think over here. So what you are saying is that every sequence of real number need not have a convergence subsequence, right? This is what you mean when you are saying this is false. So just tell me a sequence which is divergent. Still didn't get any answer. Okay, look at this sequence n. This is a sequence of real number. It has no convergence subsequence, right? Okay, and the one I think who answered a to be true, I guess you are confused with this statement. So there is another statement which says that every bounded sequence of real number has a convergence subsequence. Over here there has been nothing mentioned about the sequence, whether it is bounded or unbounded. Okay, so when you have bounded sequence, then it will have a convergence subsequence, but it's not true in general. Okay, so every bounded sequence, so to make this to make this statement true, I just need to add here bounded. So if I add bounded here, then the statement becomes true. Okay, now what about the third one? Can you give some example? Every bounded sequence of real number is convergent. Is this
1
true?
minus 1.
1 minus.
False, sir. 1 minus 1. 1 minus. Or minus 1 whole power n.
Yeah, okay. Yeah, minus 1 raised to the power n. This is a bounded sequence, but it is not convergent. Again, here the statement would have been true if you say every bounded sequence of a real number has a convergent subsequence. So then it is a truer statement. But over here it has been written that the sequence is convergent, which is not true, and you have this example. Okay, so now coming to the B part, someone said that this is true. So do you know the proof? Like, have you seen the proof of this in the lecture? I'm not sure. Hello. So have you seen the proof for the B part? You don't remember whether you have seen the proof or not? I mean, it's a standard. I think it should have been discussed in the lectures. But if you want, I can share the proof. If not, else I'll just proceed. So it's up to you whether you want the proof or not for the B part. So B part, the B statement is true. Okay, but just let me know if you want a proof or not.
Proceed, sir.
Yes.
Proceed, sir.
I couldn't get you. Can you repeat?
Sir, further proceed.
Sorry, I couldn't get.
Continue, sir. Continue.
Okay, you don't want the proof?
Yes, sir.
Okay. Okay, so now let's come to the series part. Okay, so we are almost done with the sequence. Now coming to the series, so let's begin with this easier one. So you have this sum. You have to find the value of this series. Okay. So what will be this series? So whenever you have such problem, you try to simplify it. Okay, maybe in telescopic sums or something like that. When you have to answer with two evaluation, when you have to check whether the series is convergent or not, you have to use some of the test, which I think I'll be discussing in the next session, or which must have been discussed in the session of which was from 3 to 5. In that session the other guy must have discussed it, but today, since I am lagging behind, so since I am taking this tutorial for the 5th week, so I won't be going to the test and all. I'll be discussing a bit of easy problems related to series. Okay, so to begin with, we have this example. So summation 1 by 4n square minus 1. Okay, so now to deal with this one, so over here what we have is an is 1 by 4n square minus 1. So So it is nothing but 2n square minus 1 square, and it is nothing but 2n minus 1, 2n plus 1. Okay, so over here this is the kind of factorization we get. Again, I think it's a bit lagging. So am I audible properly?
Yes,
Or
sir.
okay. Okay, so we have this kind of factorization. Now my goal would be to split it into two sums, right? Okay, so when you put this, so you know how to write it in terms of partial sum, right? So you put here 2n minus 1 and 2n plus 1, you just separate it out. And now when you want to write 2n minus 1, what will be the coefficient for 1 upon 2n minus 1? You just make it equal to 0. So you'll get n equal to half. Now you substitute it here in the other term, then you will get 2. So the factor for this, or the coefficient for this, would be 1 by 2. If you repeat the same procedure for 2n plus 1, you will get minus half, and again if you put it here, you will get minus half. So you can write minus half. So this is how you can write it in sum of two terms, right? So this is how you can write this an as a sum of two parts. Now it's a simple. So what you can do is, now you can clearly see over here. So let me write in one more line. So you'll have 1 by 2, 2n minus 1, and then you have 2n plus 1, correct? So now when you write this sum an from n equal to 1 to capital N, okay, what you see is that there will be a cancellation of consecutive two terms, correct? So these are nothing but the sum of odd terms. So after cancellation, if you see, if you put n equal to 1, you will get here 1, you will get here 3. So let me just write it once for your convenience. So what you have is 1 by 3 for n equal to 1, sorry, 1 minus 1 by 3. Then the next term would be 1 by 3 minus 1 by 5 plus 1 by 5 minus 1 by 7, and then so on. At last you will get 1 by 2n minus 1 minus 1 by 2n plus 1. Okay, so this is how the series will look like. So this is just a sum of finite terms. I am not summing it infinitely. So it's just a sum of finite terms. Now if you notice here, there is a cancellation between two consecutive terms. So this minus 1 by 3 cancels with this 1 by 3. This 1 by 5 cancels with this one, and so on. So you'll get just the first term and the last term. So eventually what you get is the sum of n terms will be just half, and then you will have 1 minus 1 by 2n plus 1. Now to get the sum of this whole series, so we wanted to evaluate this infinite sum, right? So this infinite sum is nothing but summation n equals to 1 to infinity. This is nothing but just taking limit n goes to infinity to this partial sum n equal to 1 to capital N. And now when you put limit in this finite sum, what you get is this would be 1 by 2, right? Because this term, so this term goes to 0, right, as n goes to infinity. So the final answer what you get is half, right? So this is the answer to the sum to, this is the value of this whole complete, the infinite series, right? So this is the answer, 1 by 2. So this whole series add up to get half. Okay, so this is how you can solve this series, infinite series problem. This is the simplest one, I would say. Okay. Oh, oops. Again it's lagging. Is it okay with you guys? Like, can you see the screen properly, or is it lagging? I don't know. I'm trying to move it, but I cannot see it in my laptop.
Yes, sir.
Yeah. So can you see the question number 6?
Yes, sir.
Okay. Okay. So is everything fine with the fifth problem?
Yes, sir.
Okay. So now let's move to the next problem, which is the sixth one. So in the sixth one, you have two series. Okay. So we have to check the convergence of this series. Okay. Now over here we will try to prove this convergence of these two series using the partial sums. Okay. So we'll try to establish. So for example, the first part, which is summation 1 by n, okay, that is divergent. So how to prove that? So we'll use the fact, or so let me just write one point. I think you must. So what is the definition of convergence of series? So this xn n equal to 1 to infinity is said to be convergent if if the sequence of partial sum, if the sequence Sn, which is just summation xn n from 1 to capital N, is convergent. So the convergence of series is nothing but convergence of a sequence. So when you write this series as a sum of partial sums, so the convergence of series is nothing but the convergence of sequence, right? So over here, this xn, okay, so maybe if I want to write in this notation, then let me write it as an and this as xn. So then I think it would be fine. Just a second. So k equal to 1. Yeah, then I guess it will match to this notation. Okay, so we have this xn is nothing but partial sum. So if you look at the first one, so this is partial sum of the series n equal to 1 to infinity 1 by n, right? And the second one is again partial sum of the series n equal to 1 to infinity 1 by factorial n, right? So the a and b are nothing but the partial sum of two series. Okay, so over here you just have to check the convergence of this sequence. So although this question is about convergence of a sequence, but ultimately you are trying to solve whether the series are convergent or not. Okay, so to prove this one, so the first one, I think you must have seen that this series is divergent, right? The summation 1 by n is a divergent series, correct? So over here we will try to prove that the a is a we'll try to show that the sequence given by a is a divergent one. Okay, so let's try to prove it. So we'll do it by Cauchy criterion. Okay, so we know that when a sequence xn, so let me write it here somewhere. So this sequence xn is convergent if and only if xn is Cauchy. Okay, because the real line is a complete metric space, is Cauchy, right? And Cauchy means that for epsilon greater than 0, there exists capital N in natural number such that mod of xn minus xm is less than epsilon for all n comma m greater than equal to n. Right? This is what we know about Cauchy. So over here we will try to disprove that the sequence xn, okay, given in A is not a Cauchy sequence, and it is a divergent. Okay, so let us choose for m comma n belonging to natural numbers with such that m is greater than n. We have xn minus xm. Okay, so this is nothing but, so I am choosing m to be greater than n, right? So this xn will obviously have, or maybe just write xm to be in a proper shape. So xm minus, so xm will have more terms, right? And xn will have less term, and all those xn terms will be cancelled by xm. So what you will ultimately get is 1 by n plus 1 plus 1 by n plus 2 dot 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 plus 1 by m, right? Because till n everything will cancel out with xm. So this term, like you just notice this term, how many terms are this one? So if you see, okay, to be easy one, I can write 1 by m can be written as n plus m minus n, right? So I am writing it as n plus m minus n. Then you can see that it has m minus n terms, right? Because this is the first term, this is second term, this is m minus nth term. Okay, so this is m minus n terms, and each of the term, okay, so you notice, I'll just put it here, this is equal to 1 by m. I'm just writing this last term. Okay, so this is equal to 1 by m. Now each of the term, this whole term, you know that m is greater than n plus 1, right? Because this is how you are getting these kind of terms. So all the terms 1 by n plus 1, and I mean this would imply 1 by n plus 1 is greater than 1 by m. Similarly, all these terms which are coming in between m and n can be bounded by 1 by m. So you can write here, this is greater than equal to m minus n into 1 by m, because each of the terms I have bounded by 1 by m, and this is the reason for that. Okay, so now what we have is, so if I want to write this is nothing but 1 minus n by m, right? Over here, if I choose m, so you can clearly see that it is greater than equal to some positive quantity, right? So what I'll do, so choose, just to make it fixed, so choose m equal to 2n. Then what I have is xm minus xn is greater than equal to 1 minus n by 2n, right? And this is nothing but 1 minus half, which is half. So this tells me that x2n minus xn is always greater than equal to half. That means there is a gap, so it is not a Cauchy sequence, right? So this implies that the sequence xn is not a Cauchy sequence, and hence is not convergent. Okay, so this proves that the summation 1 by n is divergent. Okay, okay, now let's come to the b part. So the b part is nothing but it's a partial sum of summation 1 by n factorial. Okay, now to prove that obviously this is a convergent sequence, because you know that 1 by n raised to the power alpha is convergent when alpha is greater than 1. So n factorial is actually increasing. Okay, it's not like increasing in like 1 by n, it is increasing rapidly than 1 by n. So in this case, like if you want to prove, so you can prove it very easily. So what we can do is, we'll try to show that this partial sums, this xn's, is bounded. So if one can show that this partial sum is bounded, then everything is fine, because we know that it is a sequence of positive terms, so it is increasing obviously, right? This is obvious. Now we'll just show that it is a bounded sequence, and hence we are done. Okay, so now how to show the bounded? So let me show it. So xn, which is 1 plus 1 by factorial 2 plus 1 by factorial n. So clearly this xn is increasing, because at each level we are adding something, right? So it is an increasing sequence. The second one is that will show, so maybe the claim is that the sequence xn is bounded. This is my claim, and one can prove it very easily. So what you can do is, so you will have to play with this factorial term. Okay, so I'll just write what is the definition of xn. So xn is 1 plus 1 by factorial 2, 1 by factorial 3 plus 1 by factorial n. Okay, now if you notice, so maybe I can write some estimate over here. Sorry. So n factorial, if you see, it is 1 2 3 4 till n, right? Over here, if I choose my n to be greater than equal to 2, so maybe I'll choose for n greater than equal to 2, I am talking. So when n is greater than equal to 2, I can write it as 1 2. Now this 3 is greater than 2, 4 is greater than 2, this n is greater than 2, right? Over here we have how many 2? So it is n minus 1, right? So we have 2 raised to the power n minus 1, correct? So now using this bound over here for n greater than equal to 2, so I can use it from here, right? So it is 1, very good. Now this is 1 by 2, so 2 factorial. So over here, like if I want to use it, n factorial is greater than equal to 2 raised to the power n minus 1. So 2 factorial is greater than equal to 2 raised to the power 2 minus 1, which is 2 raised to the power 1. 3 factorial is greater than equal to 2 raised to the power 3 minus 1, which is equal to 2 raised to the power 2. 4 factorial is greater than equal to 2 raised to the power 4 minus 1, which is 2 raised to the power 3. So in the same way, if I proceed, I will get 1 by 2, 1 by 2 square, dot dot dot, plus 1 by 2 raised to the power n minus 1, right? So we got this kind of sum. Okay, now this, if you see, this is nothing but a geometric series or geometric progression, right? So we know how to evaluate this sum. So it is nothing but a, right? If you want to write it in this term, maybe you can write it in term of geometric series. So 1 by 2 raised to the power n, where n is varying from 0 to 2. Okay, let me write it as k. K is varying from 0 to n minus 1, right? So in this case, you just write the a. So it is 1. Then you have 1 minus r, the radius, or the geometric ratio, which is half raised to the power n upon 1 minus geometric ratio, which is half. If you try to solve this one, what you get is, so this is half, so you will get 2 into 1 minus half raised to the power n, correct? Now I was claiming that xn is bounded, so you can clearly see that this term 1 by 2 raised to the power n is always less than equal to half, right? It is a decreasing sequence. So let me add one page. So what I am saying is 1 by 2 raised to the power n is a decreasing sequence, right? As n goes to infinity, it is converging to 0. So you can write it as it is greater than equal to 0 and less than equal to half, right? And this tells you that 0 greater than equal to minus half raised to the power n greater than equal to minus half. I am just multiplying by minus, and then if you add 1, you will get 1 less than equal to 1 minus half raised to the power n, and then less than half, right? This is what you get. So this whole term, this is greater than equal to half, right? So this whole I can write it as 2 into 1 by 2, which is 1. But sorry, I wanted the lower bound, sorry. So what I can say, this is less than equal to 1, okay? So this I can say is less than equal to 2. Okay, so this is what I have used here. So this is less than equal to 2, and this tells me that the sequence xn, so xn is less than equal to 2 for all n greater than equal to 2, right? Because I have used this fact here. But anyway, x1 is just 1, so there is no issue. So the xn is bounded. So this I can say this is true for all n greater than equal to 1, because x1 is 1, right? So there is no issue. So I can write this line, and this tells me that the sequence xn is bounded. Okay, So we have got a bounded sequence which is increasing. So again, by monotone convergence theorem, we can say that this sequence xn is convergent. Hence xn is convergent sequence, and this is by due to monotone convergence theorem. Okay, so see what I was telling you earlier, that this factorial thing, if you notice from here, like this is the main bound, that n factorial is greater than equal to 1 by 2 raised to power n. So you can actually use this fact. So in other words, what you can say is xn is less than equal to, so where did I show, so this part, right? So xn was less than equal to summation 1 by 2 raised to the power k equals 0 to n minus 1, right? Now if you take n, limit n going to infinity, you have limit n going to infinity, so this will be xn is less than equal to k equal to 0 to infinity 1 by 2 raised to the power k, and you know this is a geometric series which will converge to a upon 1 minus r. So a is 1 upon 1 minus half, this is half. So this xn is bounded by, I mean the limit of xn is bounded by, is equal to, is less than equal to half. So when you show so when you show that this xn is a convergence sequence, over here you can even say that the limit of the sequence is less than equal to half. This is an extra information that you can derive. Okay, but for that you have to show first that okay, this is a convergence sequence, then only you can make sense of this. Otherwise you cannot take limit. So I am taking limit here just because I have proved that this sequence xn is convergent. Once it is convergent, I can take limit, and then I can show the limit is less than equal to half. Oh sorry, it will be 2. Okay, so this is how you can get bound for the limit. So you have, anyway, you from here also you can deduce, since xn is less than equal to half, the limit of xn is also less than equal to half, less than equal to 2. xn is less than 2, so the limit is also less than equal to 2. Okay, so you don't even need this also anyway. Okay, so over here we don't even need this. So from there itself you can say that the limit of xn is less than equal to 2, just from here. Okay, but to make sense of the limit, you have to first show that it is convergent, and we have shown it using monotone convergence theorem. Okay, so we have shown that the A is convergent sequence, or the series 1 by n is divergent, not convergent. In other words, the series 1 by n is divergent, and this is convergent. Okay, summation 1 by n factorial. Okay, now let's move to the next problem, 7th one. Again, this is again easy and similar to what we have done above. So over here again we will do the same thing. We'll write this an. Okay, so what is an over here? So an is nothing but 1 upon n into n plus 1, right? So now this you can again split it and write it as 1 by n and then 1 by n plus 1, right? Now you put n equal to 0 in this one, you will get 1, so the coefficient would be 1. Now you put n equal, so if you equate it to 0, you will get n equal to minus 1. You put it here, so you will get minus 1. So minus 1 is here, right? So this product can be written in this way, correct? Again you see this is a difference of, so let me write minus here. So this is difference of two consecutive terms of natural number, right? So if you write this summation n equal to 1 to capital N, what do you get? So first you put n equal to 1, so you'll get 1 minus half. The second term would be half minus 3, 1 by 3, plus 1 by 3 minus 1 by 4, dot 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 plus 1 by n minus 1 by n plus 1. Right, this is again there will be a cancellation, so 1 by 2, right? So here where there will be some term which will cancel this. So ultimately what you get is 1 minus 1 by n plus 1. Now just take the limit. So series 1 by this is equal to limit n going to infinity summation n equal to capital N, and this is nothing but, if you take limit here, this will go to 0, so the answer would be 1. So it's similar to what we did few problems back, I think in the second last problem, I forgot. So the same idea you can apply it here and you can get the value of this sum. Okay, is this fine? So the answer would be 1. Okay, so now let's move to the next problem. So this one is quite involved, so maybe you can first try to think. So let's talk about the first part first. Okay, so over here what the question is, suppose you know, so the main, so this is one of the main condition, that the terms n or the series given here is a series of positive terms. Okay, so this is one of the important assumption over here. Okay, so over here you have to state whether the following statements which are given below are true or false. So we'll talk one by one. So to begin with, let's talk about the first part. So you have been, the question is that suppose summation n is convergent, then can you conclude, or then the series n plus 1 plus n, this is also convergent. So is this a statement true or false? This is what you have to say. Okay, so over here, like this one is quite easy, right? So do you want to think for some minute? Can you tell me, like using the convergence of n, can you tell me how you can conclude about, so I am saying that the statement is true. Okay, now can you just prove that this is convergent? So using the fact that summation n is convergent, can you prove that this is convergent? I am saying that this statement is true. Okay, so how to prove it? Any idea? Just look at the terms. Use the fact that n is positive. No? Have you seen some comparison, like, so suppose I am giving you n is less than equal to bn, okay? So and this is positive, so I am taking positive sequence. Now you must have seen this kind of thing, that now if I do summation, so summation n would obviously be less than equal to summation bn, that is for sure, right? Now I know that this is finite, I mean this is convergent, then obviously this has to be finite, there is no other option, right? Because this is a positive, I know, so this has to be some finite real number. Over here you know that this summation n is convergent, so can't you compare this one with this n? In other words, what I am trying to say, you tell me, is this true? So an upon 1 plus n is less than equal to n. Is this true? this is easy, no? Okay, the simplest way is just do the cross multiplication if you don't want to complicate anything, the most simplest one. So what does this mean? This means that n is less than equal to n plus n square. Now, do you feel that this is true?
Yes, sir.
Right, because this is a positive quantity, right?
Yes, sir.
So this is always going to be true. So this is what we have. Moreover, what we have is these are positive, and we know, so this would imply that 0 less than summation n upon 1 plus n. Okay, I can put equal to here because I don't know how it converges, so it's better to put equal to, right? And you know that this is convergent, so this is finite, so this is some finite real number. Okay, so the comparison test tells you that this is also convergent. Okay, this is by the comparison test, and it is also some finite real number. Okay, so I'll just write one line. So this is there, and summation n from 1 to infinity is finite, so by comparison test okay, so you have that this is also convergent, so this is a true statement. The second one is quite tricky, I would say. So the second one is also true. So here in the first statement what we say is if the summation n is convergent, then this is convergent. The second statement is if summation n is divergent, then this is also divergent. Okay, now how to prove that one? So again I am saying my claim is that this is a true statement. Okay, now let us see how we can prove it. Okay, so see, when you have to show that something is convergent, we need to find some upper bound, because we are in a setup of positive series. Okay, so all the terms are positive, that is very important over here. Okay, this need not be true for negative, I mean when the negative term is involved. Okay, because you know, so okay, so do you know the proof of comparison test? It's simple, right? So here I just mentioned this one, right? So an is less than equal to bn, so this would imply that summation n is less than summation bn, and this is greater than 0. So now when I say that this is finite, so this is some real number r, right? When this is finite, so this summation n is bounded, and also you know that summation n equal to 1 to capital N, if I define it as bn, then this is an increasing sequence, right? So increasing, and it is bounded as well, so this series is convergent. Like this is how the comparison test is proved. So this is how, when you want to prove something is convergent, you try to find an upper bound which is convergent. Now to prove something is divergent, what you do is summation an greater than equal to summation bn. If you know that this is equal to infinity, then obviously this has to be infinity if it is positive terms, all the terms are positive. So over here I am saying you that all the terms are positive, we have this assumption that all n's are greater than equal to 0, greater than 0 in fact. So to show that this is divergent, you need to get a lower bound with n, right? So we have to get some lower bound, so that we can show that using comparison test we can say that this is also divergent. Okay. Okay, so this was just the rough idea. Okay, so now let's try to find some lower bound for the sequence an upon 1 plus an. Okay, so what you have is summation an is divergent. Okay, so what I'll do over here, we'll try to split this in two cases. Okay, so the case 1 is when an is greater than equal to 1 for infinitely many n's. Okay, and how to do that? You know that in this case, if an is greater than equal to 1, you just keep this thing in mind. Okay, where is it? This term. Okay, so when an is greater than equal to 1, this would imply for infinite, I am saying, this will tell me that 2an is greater than equal to, so this 2an is nothing but an plus an, and this is greater than equal to 1 plus an, and this would mean that an upon 1 plus an is greater than equal to half. Right, so we have found some lower bound. So this is for infinitely many n's. Okay, I'm not saying this is true for all n, so this is for infinitely many n's. Okay, now once I have this kind of bound, this will tell me that this limit, if I want to take, this is not going to be 0, because if I say that the limit is 0, then that would mean that this term is close to 0 for infinitely many n's. Right, after a certain point, what do we mean when we say that limit of some xn is 0? This means that xn is belonging to this minus epsilon epsilon neighborhood for all n greater than equal to capital N, right? But since I know that this is greater than half for infinitely many n's, so the limit cannot be 0. Correct? So this is one way of arguing. I'll tell you another way maybe. Okay, so this proves that the limit is not equal to n, and this will prove that the summation an upon n is not convergent. So this series is not convergent, right? This is a necessary condition. I hope you know this, that summation xn is convergent implies that the limit xn, okay, is equal to 0. This you must have seen, that if a series is convergent, then the nth term must go to 0. So since the nth term is not going to 0, you cannot say that so you cannot conclude about, or you can conclude that it is not a convergent series, because if it is convergent, then the limit has to be 0, which is not true here. Okay, so this is one way. The other way could be, like as I mentioned, you have found the lower bound, but that argument, okay, let's see. So we have found this kind of upper bound. Then if you want to write this an upon 1 plus n, right, n equal to 1 to infinity. So suppose this is for infinitely many n, so I am calling that set of n as S. Okay, so let me write. Okay, so I am defining S to be n belonging to natural number such that n plus 1 plus n is greater than equal to half. Okay, then this is greater than equal to n belonging to S, n upon 1 plus n, right? Because this contains all the term, and here I am taking only those terms which is greater than half, and now this is greater than equal to half, and then summation n, any cardinality of S, and you know that the cardinality of S is infinite, right? Because this set S is an infinite set, right? This is what we have mentioned here. So this is equal to infinity. So this series cannot be convergent, it is divergent, right? So this is how you can use the lower bound. So you need, when you have this lower bound, you can conclude this fact. Okay, so over here notice one thing, here we have not used the fact that summation n is divergent, right? I have not used anywhere, But this is just a case 1 where I have a stronger assumption that the all the terms is greater than equal to 1. That is a strong assumption that I have taken here, case 1. Okay, so the case 2 is the much more, I would not say, case 1 is very vague, because when you have summation n equal to infinity, n greater than equal to 1 is a very strong assumption. Okay, so that's why we did not need to use this one. But in the second one, I'll have to use it. So the case 2 is that an is greater than equal to 1 for finitely many n's. That means that n's are strictly less than 1 for infinitely many n's. Okay, so what I can write is, this would mean that an is less than 1, or this way, there exists some natural number such that an is less than 1 for all n greater than equal to n, right? Because it's just finitely many n's, an is greater than equal to 1. After that, it has to be less than 1. Okay, this would mean that 1 plus an is less than 2, and this would mean that 1 upon 1 plus an is greater than half, right? And thus, okay, and this would, so I'll just multiply by an here. So an upon 1 plus an is greater than equal to an by 2. And now again I'll use the same argument. So if I sum it here, summation an upon 1 plus an is greater than equal to summation n upon 2 n from 1 to infinity. So this half I can remove, it's not an issue. So half I'll take common and bring it out. Okay, now you know that this series is divergent, so this sums up to infinity, and so this tells you that summation an upon 1 plus an is equal to infinity, or diverges. Okay, is this clear? So see, this is a very stronger assumption what I've taken here, that all the terms are greater than equal to 1. This is much more stronger. Okay, but this is the more natural one, that an can be less than 1 also for infinitely many n's. Okay. And this is where we need to use the fact that summation n is infinity, or summation n is divergent. Okay, so these two cases we have done. Now what about, so is this clear, like the first two statements?
Yes, sir.
Okay, now let us come to the third one. So the third statement, what it says, that suppose summation n is divergent, then is it true that n upon 1 plus n times n, so this is the extra term what we have, is this also divergent? This is a bit complicated, but in some sense it's easy also. Okay, when you get to see the example, then it will be obvious to you. Okay, so this statement is false. Okay, so I'll try to find an an such that the summation n is infinity, but this becomes finite, or this is convergent. Okay, so what one can do is, see over here, so let me just write, so n you have to find such that this becomes infinity, but the advantage what you get here is n times an. This is the advantage what you get, right? So you know that summation 1 by n is divergent, right? Or just, if you just take n equal to n, if you take n equal to n, you know that this is divergent. But when you put n equal to n here, let's see what happens. So you'll get n upon 1 plus n square, right? So if you forget about this 1, so it is 1 by n. This is again divergent. So we are not done yet, right? So we'll try to do a bit of change here. So if you notice carefully, whatever power of n, so if even if I take n square, so here I'll get n square and here I'll get n cube. So I'm forgetting about this one as of now, okay, because this is just a constant translation. Okay, so let's not worry about this one. So over here we'll get a and n is also always going to cancel, if you notice. So whatever n you choose, you will get 1 by n only, kind of, right, if you forget about this one. So we have to define it in a very proper way, okay, so that everything works fine. Okay, so we have to take advantage of this n in such a way that this whole series is convergent, and this is how we try to do. So now let's come to the example. So you define an, okay, you make it 0 when n is not a square, okay, so that means this is 0 if n is not a square of some natural number, okay, for some m belonging to n. If it is a square, that means if n is equal to 1 or 4 or 9, so if n is 1 square, 2 square, 3 square, 4 square, in that situation you put n is equal to m square. So basically you just put n equal to n if n is equal to m square for some, okay. Now if we define my sequence in this way, let's see what happens. So it is clear that summation n, if I do, this is nothing but, so n equal to 1 to infinity, and this will be nothing but 0, and then you will have m square, m equal to 1 to infinity, which is infinity, right? So when n is m square, it is just simply m square, okay. So this is how we get that it is divergent. But now let's look at this summation n upon 1 plus n times n. Okay. In this case, if you see, when n is 0, we don't need to worry, okay. So when n is equal to, when n is equal to m square, what do we get? So we'll get here m square. So let's write m is equal to 1 to infinity. So n is m square, and in below we'll have n is equal to m square and then m square. Now can you see there is a rise in the power? Earlier this n times n was there. Now we have m square times m square. So basically this is what I have done. When n is m square, I am making it a power, one more power, I am increasing the power, right? So this n upon n times n, when now this cancels out, I am getting 1 by m square, and that's why I have defined the sequence in this way. So now this n is 1 by m square actually, okay. So that is the change what has been done over here, okay. Yeah, so this is what I was saying, a and n will cancel, you will get just n. So summation 1 by n is divergent, this is equal to infinity. But if I put n equal to m square, I am getting 1 by m square, m equal to 1 to infinity, and this is finite. So I am making 1 by n equal to 0 when n is not a square, otherwise I will put 1 by m square like that, okay. So this is the change. Okay. This is very important actually, this idea, okay. So this is what we have. Now you can clearly see this is nothing but 1 by m square by 1 plus m raised to the power 4, m from 1 to infinity, and this 1 by this I can dominate by m equal to 1 to infinity, m square by m4, right? Because 1 I can remove, 1 plus m4 is greater than equal to m4, right? So using this I will get this. Now this m square will cancel with m4, so I will get 1 by m square, and this is finite. So this series is convergent, right? So we have got an example where summation n is infinite, but this series summation an upon 1 plus n times an, this is finite. Okay, now d is much more easier. So in d you don't have to do anything at all. Okay, so look at the question. In d you have been already given this is n square, so the situation is much more simpler. Just take n to be n. Okay, so this is again a false statement. Okay, so over here you don't have to play with this trick. You don't need this trick at all. So in d you just simply take an equal to n, then what you have is summation an is infinity, but summation an upon 1 plus n squared time n, if you do, you will get summation n 1 plus n cube, sorry, right, and this is less than equal to summation n upon n cube, and this is 1 by n square, and this is finite. So in d part you don't need to do any kind of manipulation, or you don't have to do any trick. It is very simple in d. Okay, is this clear? Do you have problem with any of these 4 statements? It seems you have some doubt. You can ask me if you have some.
Sir, what happens if we choose an to be n square throughout? You have distinct it as equal to 0 if n is not equal to m square. What happens if we choose an to be n for all the
This
terms?
is what you, okay, so this is what I said. So suppose if you choose n equal to n, see what is this series? Let me write. See, I have been given this summation an upon 1 plus n times n, right? No, just forget about this n. Okay, just look that this is this 1, we don't care. 1 is, you see, 1 is not playing any role. I am just removing 1 over here. The same I have done here. So 1 is not important. Okay, so see, when you have this kind of thing, whatever n you choose, it will be 1 by n, right?
Yes, sir.
Then it is divergent, I know. That is why what I am doing over here is, so this cancellation an can be done only when n is 0, right? N is non-zero. If n is 0, then this cancellation does not make sense. This whole thing is 0, right?
Yeah.
Right, so that's why what we are doing,
Yes.
we are putting n equal to 0 when we have n is not proper square. When n is proper square, what we are doing is we are making it n square in some sense, right? And then this cancels, then you have 1 by n square, and then it's okay, then you have the convergence.
Okay, sir. Fine, sir.
This is what has been done here. In the, if you see in the d part, you don't have to do all those tricks. Whatever n you choose, we don't care at all. It is divergent, that n will cancel, so you have 1 by n square automatically, and that's enough. So if you choose n equal to n, then it's very easy. You will get n cube. This n and n cube will cancel to get 1 by n square, and then it's finite. Okay, this is the main difference between D and C. Okay. Okay. Then now let's come to the second part. So this is the problem related to Cauchy condensation test. Okay. And this, I have seen that this has been discussed in the lecture, I guess. okay, as far as I remember. So this Cauchy condensation test is nothing but it says you that this roughly that this summation xn is convergent if and only if the summation 2 raised to the power n x to n is convergent. Okay, this is what this Cauchy condensation test is. Okay, you have seen this statement probably in the class, but I don't know whether this name was mentioned or not, but you have seen this result. Okay, so using this result we'll try to solve these problems. Okay, so let's come with the first problem. So you have to show this summation n equal to 2 to infinity 1 by n log n raised to the power alpha, is this convergent or not? So this is convergent if and only if, as this statement tells you, that n equal to 2 to infinity 2 raised to the power n times x 2n. So this is xn, right? So x 2n would be 1 by 2 raised to the power n log 2 raised to the power n times alpha, right? This 2 and 2n will cancels. So this is convergent if and only if this is convergent, and this is convergent is another way of saying that log n equals to 2 to infinity. If you use this log property, so what you get is n times log 2 raised to the power alpha. This is convergent, right? You just take log 2 outside, right? So one can do that. So okay, so this is another way of saying 1 by log 2, because that is a constant term. So log 2 raised to the power alpha, and then summation n equals to 1 to infinity 1 by n raised to the power alpha, right? So this is finite if and only if this series is finite, right? Because this is just a constant term, so we don't care about this. So this convergence is true if and only, so you can forget about this term. So maybe I will put some other color. If and only if this is convergent, and this is convergent if and only if alpha is greater than 1, right? This you have already seen. 1 by n raised to the power alpha is convergent if and only if alpha is greater than 1. Or you might have seen in this way, 1 by n raised to the power p is finite if and only if p is greater than 1. Right? So this is p series test, or sorry, p, I forgot the name, but
P test, sir.
uh-huh.
P series test only, sir.
P series test, okay. So this is what you have, this result, right? So we know that this is true if and only if alpha is greater than 1. So this is fine. So this is convergent, this one is convergent if and only if alpha is greater than 1. Okay, otherwise it diverges. Okay, now let's come to the B part.
What about alpha equal to
1?
Equal to 1 means the test fails, no, sir?
Sorry.
If alpha equal to summation 1 by n power p is convergent if p greater than 1, and if it is less than 1, it is divergent. What about equal to 1, the test fails, no, sir?
No, that is also divergent, right? So 1 by n, I just mentioned 1 by n is divergent. This is equal to infinity. In the last example I mentioned you, right? This, I mean, I mentioned somewhere that 1 by
Yes,
n is the
yes, sir.
problem, right? So this is divergent if alpha is less than equal to 1. So you have that equality is also there.
Okay, sir.
Okay, so you have this one, and now let's go to the second part. So B is, again I'll use the Cauchy condensation test. So you have 1 by n, so summation n equals to 3 to infinity 1 by n log n, you have log n. Okay, so this is convergent if and only if, I'm just again using the same test, Cauchy condensation test, if and only if 2 raised to the power n times x to n. So this is your x n, so x to n would be 1 by 2 raised to the power n log 2 raised to the power n, and then log 2 raised to the power n is convergent. So again, if you write this one, you will have summation n equals 3 to infinity 1 by n times log 2 and here you have log of, okay, so log of n log 2. Okay, so if I write it again, this is nothing but summation n equal to 3 to infinity 1 by n, so log 2 I will just write outside maybe, so 1 by log 2 times, this is n times, if I break this log, so I'll get log n plus log 2, right? So this is convergent if and only if this is convergent, and this is convergent if and only, so again I'll use the Cauchy condensation test. So this is convergent if and only if log 2 summation n equals 1, sorry this was 3, 2n into, so now this is again your xn, so 2n upon xn, which is 2n log 2n plus log 2. Okay, if and only if this is convergent. And now again if I write it out, this is log 2 summation, so this 2 and 2n cancels, so over here you will have n times log 2 plus log 2. Only if this is convergent. Now you know like this is just a constant, so it does not matter much in the convergence of the C series, and this is again a constant, so it is more like, this behaves like 1 by n, which is divergent, right? So since this summation 1 by n, we know that this is divergent, so I mean this is more like, so you can write this maybe this symbol, so this behaves like 1 by n, right? And we know that the summation 1 by n is equal to infinity, so the series summation n equals 3 to infinity, what was that, 1 by n log n log n, 1 by n log n log n, this is divergent. Okay, so this series is divergent. So here we have used the Cauchy condensation test twice, so by Cauchy condensation test, so once I used here and here also. Cauchy condensation test. Okay, so we have solved this one. Now let's move to the last problem for today's session. So again this question is related to evaluation of this sum. Okay, again this is not too tough, like you just have to write this an's properly. So over here you see, so what you have is an is given as n square minus n plus 1 upon factorial n, right? Okay, so again you do the same thing, you just split it into two parts. Okay, so over here you don't have that product thing, so it's very easy, so just distribute n factorial in this one, so you can write this n square minus n upon n factorial plus 1 by n factorial, right? Okay, now this, if you see, this is n into n minus 1, and then you have n factorial plus 1 by n factorial, so this is nothing but this is 1 upon n minus 2 factorial, right? Correct. So this is true when n is obviously greater than equal to 3. If n is equal to 2 or n greater than equal to 2, then you can do this. Correct? So for n equal to 0 and n equal to 1, this is 0, this term, so it doesn't matter. This is 1 by n factorial. Okay, so this summation n square minus n plus 1 by factorial n is nothing but summation. So this is n equal to 0 to infinity n into n minus 1 by factorial n factorial n. Okay, so now I'll just rub this off. Correct? Now this is equal to summation n. So for n equal to 0 this is 0, for n equal to 1 this is 0, so n equal to 2 to infinity n into n minus 1 upon factorial n plus summation n equal to 0 to infinity 1 by factorial n. And now this is again, as I mentioned earlier, this is nothing but 1 upon n minus 2 factorial. Right? Now again, if I do a change of variables, so I'll get, so I am putting n minus 2 as m. So m will vary from 1 to 0 to infinity. This is 1 by m factorial plus this is n equal to 0 to infinity 1 by n factorial. Now you remember that this exponential x is given by summation x raised to the power n upon n factorial, right? This is the formula for exponential. If you put x equal to 1, you will get e1 is summation n equal to 0 to infinity 1 by n factorial. Right? This is the formula. Now if you substitute, put it this one here, you will get e. So this sum is to e. Again this sums up to e. So you'll get 2e. Right? So this whole series sums up to 2 exponential 1. I mean 2 times exponential e raised to the power 1. Is this okay?
Yes, sir.
Okay. So do you have any doubts from these problems? Any of the...
Not in this problem, sir. When we have given a problem, how do you choose that we have to apply the Cauchy's condensation test and comparison test? How do we know, sir?
No, see, like it will come after some experience, but as far as, for example, this Cauchy condensation test, whenever you have to use, you can notice one thing, that this n will always be there. Because then, I mean, in most of the problem, if you see, this n will be in the denominator, so that when you take 2n times x to n, this 2n to n will cancel. Now you will just have this term. Okay, so generally this test is used for logarithmic kind of function. Okay, this Cauchy condensation test. I am understanding your problem. So what your problem is a bit more general, like when to use ratio test, when to use limit comparison test, when to use integral test, all this kind of things. So in that scenario, basically it will come after some experience. Okay, like, or so any series test can be used. So for example, like here I have used the comparison test, but okay, that's not, let's go to some problem. Actually in today's session I have not included any problem where I can discuss the test, but what I am trying to say, that you can use any of the test, whatever suits you. Okay, if you get a hint that okay, I can use here comparison test, just by if you find some proper upper bound, if you get some proper lower bound, then it's very easy to use the comparison test, right? Because suppose you have been given some an, if you are able to find some constant times n square, okay, then you know that this is convergent, so this is convergent. If you are able to get some lower bound with c times n, then you know this is divergent, so this is divergent. Okay, so in case if you are knowing some result, so generally when you do the comparison test, you use this kind of limits, I mean this kind of bound. So 1 by n raised to the power alpha. When alpha is greater than equal to 1, you try to get the upper bound, or for alpha less than 1, you try to get a lower bound to conclude convergence and divergence. So this is about the limit comparison test. Comparison test. Now when it comes to limit comparison test, you have to find a proper sequence Bn. So for example here, like I was somehow I was hinting you here. Let me go back to this problem. Where was I mentioning this one? Yeah, here. Over here I was telling you, right, this kind of argument I was giving you, an upon 1 plus n times n. I was saying you just forget about this 1, right? Because, or here also I mentioned, over here I said that this term is more like 1 by n, right? So in this kind of situation, when you have some constant and when you see that this series is behaving like this kind of, it has this kind of behavior. For example, if here it was n 3 by 2 or whatever power it has, when you have that, okay, it has a behavior of this kind, then in that situation you use the limit comparison test. So you define Bn to be this. So this was your a, or this was your an, define Bn, try to find the limit an by Bn, and then you see what the limit is coming. Then using that limit comparison test, you can conclude about the convergence. Okay, so this is, so when I am saying that this behaves by like 1 by n, this can, so convergence or divergence of this thing can be proven using the limit comparison test. Okay, now if you go to, let's say, what other tests are, a ratio test, right? Ratio test, so, or nth root test. So when you have this power, like something an has some, so an is something like something is there raised to the power n, this kind of thing, then you use the nth root test, that you take n upon 1 by n, this kind of thing, and then you try to find the limit, right? In some cases it's better to deal with n plus 1 upon n, this kind of ratio, then you use their ratio test. So you'll experience it when you try to solve more and more problems. You'll get to understand like when we are using what. When I was also studying this kind of thing, then I also had this kind of problem, like when to use what. So that is a very obvious problem, but you will understand when you get a bit hand on it. You will understand what to use and when.
Thank you, sir.
Okay. Okay, then let's see you on next Tuesday. Okay, and sorry for the postponing of this lecture. I had some issues, so I postponed it to Saturday. So see you next Tuesday then. Then there I'll be talking more about sequences and test, all these things. Okay.
Thank you, sir.
Okay then. Bye.